about alternating series test. This is the second to the last test that is going to be assessed on the AP for you guys. So let's take a look. I did post the full notes that go with this section, and we are going to circle back to this after the AP, depending upon our schedule and when the AP happens. So an alternating series is a series whose terms are alternating positive and negative, positive and negative. And we can see that in the summation notation by taking a look at these parts right here. This is the key that these are alternating, where we see a -1 to the n plus 1 power, and when we see a -1 to the n power. It can really be anything, n plus 1, n plus 2, n plus 3, whatever it's going to be, but most often than not, it's one of these. And this is helping us to identify if the first term is going to be negative or if the second term is going to be negative. Because if you're putting in 1 for n, this squares it, which means this becomes positive. If I'm putting 1 in for n, this is -1 to the first power, so we're going to start with the negative and then go positive, negative, positive, negative, and it continues till we keep on going. Up here we've got a positive leading, and then we're going negative, positive, negative, positive, so this is alternating. So when we're taking a look at the limit as n goes to infinity of a sub n, and of course this is our a sub n, if it equals 0, it tells us very little about the convergence of the series. If it turns out to be an alternating series, then it must converge if the terms have a limit of 0 and are decreasing in magnitude. Series test, also known as Leibniz test, and this is reference to lots of old calculus textbooks, implies that a sub n has to be greater than 0, and that's excluding the alternating part, so that doesn't include the -1. Then the alternating series, whether it's -1 to the n power or -1 to the n plus 1 power, converges if the following two conditions are met. First, the limit as n goes to infinity of the term is equal to 0, and this next term is smaller than the original starting term. So that means it's decreasing in magnitude. Each and every time the absolute value of the term is getting smaller. And thinking about this in terms of how you guys are going to have to represent this on the AP, being it all free response, they are specifically going to be looking for these three things to happen if you'd like to prove with this test. 1, you've got to have alternating signs. 2, you've got to show it's decreasing in magnitude, and that's that part right up here. And 3, the limit as n goes to infinity is equal to 0. Be aware of this. This does not say that if the limit as n goes to infinity of the function doesn't equal 0, that does not imply that it diverges. This test can only prove convergence, which is almost the complete opposite of our other one that can test for divergence. So if the limit as n goes to infinity doesn't equal 0, we can say the series diverges by the nth term test, not by the alternating series test. So this is one of those things that you are going to have to be very careful about when identifying how you're proving a series converges or diverges by taking a look at the conditions that need to be met in order to use it, and also what it's really saying. And it's going to be pretty easy to test if you know it or don't know it. So let's take a look at a couple examples. So here's our first example. We've got the summation from n equals 1 to infinity of -1 to the n plus 1 power times n over 2n minus 1. So we can take a look at this. So we've got our alternating portion, and if we just want to plug in just so you can see what's happening here, we've got 1 being our starting point, so we've got -1 being squared. We've got 1 divided by 2 times 1 minus 1, so we would have 1. Next term would be plugging in 2, so negative 1 to the third power would be a minus. So we'd have 2 over 4 minus 1, which is 3. And my Mobi's broken, so bear with me. Next one, we've got a plus. And we would have 3 over 6 minus 1, which is 5. So as you can see, all these terms keep alternating. And then we would have a minus, and as we continue, we can also see that they are decreasing. So we've got our second condition met, that they are decreasing in magnitude, but let's check the first condition. So we want to see if the limit as n goes to infinity of our function. So we don't need the alternating part. All we're looking is at the a sub n part, which is n over odd numbers, 2n minus 1. And we're taking a look at this as the limit as n goes to infinity. So we're dividing each term by n, because that's our highest power in the denominator. And as n goes to infinity, our numerator is 1 over 2 minus 0. So this equals 1/2, which does not equal 0. So what that tells us is this series diverges, and it doesn't diverge because of the alternating series test. It diverges by the nth term test. So let's take a look at the next example. We are having an alternating series, and we can tell that because we've got our -1 now to the nth power. So we are alternating, so that's our first check. Decreasing in magnitude. So let's write that out. We've got our first checked that we are alternating. We want to check to see if it is decreasing in magnitude, and if I plug in 1, I get 1 over 1 squared. And then if I plug in 2, I've got 1 over 4. And if I plug in 3, I've got a 9th. So we are decreasing in magnitude. So that means our next term is less than a sub n. And now we want to test our third one. And we want to check to see the limit as n goes to infinity of our term. So 1 over n squared, our a sub nth term. So as we're taking a look as n goes to infinity, this does happen to equal 0, which means this converges by the alternating series test. This is for our notes and where we're going to stop today. The rest of the notes that are included are ones that we're going to be picking up after the AP exam because they are not going to be assessed this year. So proving absolute convergence and conditional convergence for alternating series, as well as taking a look at the alternating series error bounds. I want to walk you through a couple examples of why those conditions are important for the alternating series test. So for an alternating series test, it has to be alternating sign, decreasing in magnitude, and the limit has to equal 0 as n goes to infinity. So on this one, you've got an example of a series that is alternating, positive, negative, positive, negative, positive, negative. And if we take a look at the next term compared to the third term compared to the second term, 1/3 happens to be greater than 1/4. So this is not decreasing. And in fact, this series diverges by the p-series test. And another example that we have on here is another positive, negative, positive, negative, positive, negative. The a sub nth term is right here. And that's what we see. We've got 1/2 to the first minus 1/3 to the first, 1/2 squared minus 1/3 squared, and that next term is not smaller than the previous term. 1/8 is greater than 1/9. 1/16 is greater than 1/27. It does work right here, but it doesn't work continuously the whole way. But this one does happen to converge because the geometric series, so it's 1/2 to the nth power and 1/3 to the nth power, and the sum or difference of two convergent series also converges. But that's another one where you can't prove by the alternate series test. We also can have series that are alternating sign and decreasing, but do not have a limit as n goes to infinity of 0. And this we cannot say diverges or converges by the alternating series test because we don't have those conditions met. So we have an alternating term, -1 to the nth power. We've got n plus 1 over n, so 3/2, 4/3, 5/4, 6/5. Each time the next term is getting smaller. But if you take a look at the limit as n goes to infinity, you get 1 instead of 0. And this series diverges instead of converges because the limit of the individual terms is not 0, and the positive terms are approaching 1 while the negative terms are approaching -1. So this would diverge by the nth term test. Again, you don't have your three conditions met to prove by the alternating series test.